Sina? Okay. Okay. Hello. So number 412. Are you getting my voice? Hello.
Yes, sir.
Okay. Okay. All right. Why only remaining people where? Where is the remaining
Oh,
people?
thank you, sir.
That message went to all the peoples, na? Invitation. Okay. Okay. I'm going to start. I'm starting the class. Okay.
అమ్మాయి నారా చదవచ్చమ్మా కొద్దిగా ఈ పొడుగు పెట్టమని మళ్ళీ ఉతికాలకు దానాది సరిపోదు కొద్దిగా పొడుగు పెట్టం ఒక్కరో ఒక అంగుళం పెట్టమని మంచిగా నలుగురు నూనె చాలా కేజీ ఇచ్చేది మంచిగా కేజీ ఎంతసేపు పట్టాలా మీ నాన్న ఇంకా పని లేనప్పుడు చిత్తపడు
Okay. So good morning to one all. So
Good morning, sir.
good morning. So are you observing the slides? Are you visible? Are you visible the slides? Are you getting the my sharing? Hello. Hello. Okay. So in the last class we are discussed about the different characteristics of an instrument. The mainly two types of characteristics are there: static and dynamic characteristics. So coming to static characteristics, we have the major characteristics are accuracy, precision, sensitivity, resolution, threshold, hysteresis, reproducibility, drift, repeatability, linearity, dead time, dead zone, scale range, and scale span. These are the major static characteristics of an instrument. And in that, the first one is accuracy. Accuracy is closeness with which an instrument reading approaches the true value of the quantity being measured. So it represents the how much closeness of the measured variable with the real value. Okay, so there are three types of measurement accuracies. So we can represent accuracy in point accuracy, accuracy as percentage of scale reading, accuracy as percentage of true value. And coming to precision, so precision is a measure of the degree of agreement within a group of measurements. So here, if you do the number of experiments on a particular variable, so we will get the number of measurements. So in that, we have an agreement how much those values are nearer or closer to each other. Okay, so here measure of the degree of agreement within a group of measurements. Suppose you are going to measure a voltage. Okay, so you are using a voltmeter, measure the voltage of an instrument or equipment, you will get the value of 50 volts. Suppose you came to measure the same value, measure the voltage of that instrument. If the instrument produces the same value, 50 only, and again after some time you came to measure the same quantity, the same instrument, and you get the same value, that is 50 volts. 50 volts, then you can say that that instrument is having a precision, highly precision, because every time it is showing the same value. It is showing the same value. So here, so we can relate the accuracy and precision. So accuracy represents the degree of correctness of the measured value with respect to the true value. So this is accuracy is degree of correctness, whereas precision is degree of agreement. So on the other hand, precision represents degree of repeatability of several individual measurements of the desired input, all the at the same reference conditions. So the main thing in precision is we have to maintain the same reference conditions for every time when you are measured the quantity. So the precision measurement may not necessarily be accurate and vice versa. It means you have done a measurement that is obtained precision measurement may not be an accurate, or similarly an accurate measurement may not be a precision. See, the one example is here to represent this statement. So suppose a person is doing a shooting practice on a target. So he can hit the target with the following possibilities as shown below. So there are four possibilities. Suppose a person is doing shooting practice and the center circle is the target. So it should be hit the bullet at this center point. So then only we can get the perfect shooting. Okay, so the first case, see here, all the bullets are at the target. Okay, and here we have four bullets. Four bullets are at the circle, that is the target, and um, and four bullets are very nearer. So that's why the accuracy is very high. Accuracy is high and precision is high. So coming to next case, the here in this case, the bullets are hit at the outer circles. So due to that, so the accuracy is deviated. So accuracy means we have to hit the at this position. So then we can say it is accurate point. So but the all the bullets are shooted at the outer circles, but the bullets are very near to each other. So it means the accuracy is low and precision is high. Accuracy is very low, okay, and precision is very high because all the bullets are hit at the same place, nearer to same place, okay. And coming to third case, so in this case all the bullets are very far away from the very far from the target, and also one each other it is very different. I mean, there is a large difference between one another. So due to that, the precision is low and accuracy is somewhat high, very near to target. And coming to here, so here the precision is very low because all the bullets are very far away, and and these bullets are very far away to the center point or target. So that's why in this case accuracy is low and precision is also low. So from this figure we can say that a precise measurement may not be an accurate. This is the precise measurement, but it is not accurate to the actual point of the measurement. So this is the difference between accuracy and precision. Okay. And coming to static sensitivity, this is another characteristics of an instrument. The static sensitivity of an instrument is the ratio of the magnitude of the output signal to the magnitude of the input signal, and it is also inverse of sensitivity is also called as scale factor or deflection factor. Slope of the calibration curve also defines as the sensitivity. So we will see in the next slide. So this is the following figure shows the sensitivity measurements. So here this is the a curve, and it is having a change of input. For this change of input it is having change of output. So it is the sensitivity means the change in output signal to the change in input signal. So for a delta change of delta qi, for delta change in qi, there is a change in the q naught output. So that is the change in output to signal to change in input is the sensitivity. And inverse of this sensitivity is the scale factor or deflection factor. So inverse sensitivity is nothing but inverse of this one, dqi by dq naught. So sensitivity of an instrument should be high because for a small change of the input signal we have higher change of the value. So if the sensitivity is very high, we will get a larger output for a small change in the input. For a small change in the input. Okay. So coming to resolution. So if the input is see here, if the input is slowly increased from some arbitrary input value, not zero. Here the case is we are not increasing from zero, we are increasing from some non-zero value, it may be 1 or 2 like that. So then the output does not change at all until a certain increment is exceeded. So we does not get the output until the input is changing certain amount of the for changing the input amount of the input increasing, until that we don't get any output. So that small increment will be considered as resolution or discrimination. Suppose we are increasing a value of input, so but that instrument does not shows the output until a certain increment in the input. That increment is considered as a resolution or discrimination of the instruments. But here the case is non-zero. So we are not increasing from zero, we are increasing some other values, non-zero values. So smallest increment in input, the smallest increment in input which can be detected with certainty by an instrument is its resolution or discrimination. So here we have some example. A moving coil voltmeter has a uniform scale with 100 divisions. The full scale reading is 200 volts, and 1 by 10 of a scale division can be estimated with a fair degree of certainty. So determine the resolution of the instrument in volt. Suppose we have a scale 100 divisions, we have a meter, analog meter, so it is having 100 divisions, and with that 100 divisions we can measure the 200 volts. We can measure the 200 volts up to that. So then each division will measure how much value? So 100 divisions, 200. So each division will measure a 2 volts, and 1 by 10 of the scale division can be estimated with a fair degree of certainty. They determine the resolution of the instrument. So here we have 100 divisions, and with that 100 divisions we can measure the 200 volts. So due to that 200 volts by 100, that is 2 volts. For each scale division we will get the 2 volts, and resolution is 1 by 10 into scale division. Here 1 by 10 of scale division is the resolution, and one scale division is 2 volts. 1 by 10 into 2, it gives the 0.2 volts. So this 0.2 volts represents the resolution of the instrument. Okay, and coming to threshold. So threshold. So if the input is increased, input of the instrument is increased very gradually from zero. So see here, threshold, for threshold, so we have increased the input gradually from zero, whereas for resolution non-zero, it means we are not increased from zero, we are increased from other values, non-zero. Whereas for threshold, when the input is increased from zero, so until certain amount of value change in the input, we don't have any output. So that minimum value determines the threshold of the instrument. Okay, so here, so we have a, we increase the value of the input. For that increase of the input from zero, so until certain amount of the increment in the input, so we don't have any output in the instrument. That will be considered as a threshold. Suppose here we have, suppose uh, suppose here we have a uh, driving network driver. So here this is the driving gear and this is the driven gear. So this driver gear will latch in this particular gap, and it will drive this driven gear. Okay, so whenever these gears will be insert here, so and whenever this gear is rotated, and attached driven gear also rotated. So to make this gear rotation, so see here, so initially we have a difference of some x difference between these two to get connected with the driving gear and the driven gear. So until this driving gear is moves this much of distance, we don't have any movement in the driven gear. So this much, this is called as backlash. Backlash is observed in the gear system. So whenever this driving gear will move a amount of x distance or backlash amount of distance x, so this gears will be fixed in the driven gear. Then only this driving gear will drive the driven gear and rotates the further attached movable devices. So for mechanical instruments, the first noticeable measurable change may not occur due to the backlash. Okay, above figure shows the gate train. So uh, there is not noticeable change in the driven gear movement until the driving gear moves through a distance of x, which is backlash the gear. And coming to dead time. So dead time is defined as the time required by the measurement system to begin to respond to a change in the measurement. Suppose, see here, this in the figure here we have a dead time. This is the dead time. So this is the time, and this is the output. Okay, measure this is the output. Okay, so until certain amount of time we don't the instrument does not respond. Okay, so actually this is the curve for the this is the curve measured quantity. Actually we have to measure this much of quantity, but the measurement instrument does not respond until the quantity will be changes up to this point. So up to that point the instrument having zero output. So at the this time the amount of the time taken for the instrument to respond to the input, so that amount of time will be considered as a dead time. Dead time is defined as the time required for the measurement system to begin the response to change in the measurement. Okay, and coming to dead zone. So dead zone is nothing but the largest change in the input quantity for which there is no output of the instrument. Suppose how much, see, this is the up to this point there is no output of the instrument. The instrument does not respond yet. So this amount of change is occurring until that there is no output in the instrument. So how much amount of the instrument, how much amount of quantity the instrument is waiting or not responded, that amount of zone is considered as the dead zone. So this amount of zone, okay, so that is called as the dead zone. So no output of the instrument. It is defined as the largest change of the input quantity for which there is no output of the instrument. We are increasing the input, but instrument is not responding. So how much you are increasing the input up to respond the instrument, that change of the input change or maximum change. So that can be considered as the dead zone. For example, the applied input may not be sufficient to drive the overall section of the instrument. So in some cases, so the machine, the instruments having some frictional forces. So suppose we are applying the input, but due to having friction of the instruments, so it does not respond it to. So we have to increase the input value to respond or to overcome that friction. Then only the instrument is responding. Instrument is responding. And coming to hysteresis. Hysteresis. When the input of the instrument is slowly varied from 0 to full scale and back to 0, the output does not coincidence or not same when the input is increased and then decreased. Okay, suppose we are going to measure increasing value of input. Suppose the input is increasing and we are measuring the output. Suppose here this is the input is increasing, output is also increasing. Up to here we are increased. So that process is, you can call it as loading. Now the input is decreasing. Now the input is decreasing, but the output also decreasing. Output is also but decreasing, but it is not following what we are increased situation. When the input is increased, the output is this one. But when the input is decreases, the output should follow the same path what we are observed when it is increasing. when the input is increasing. When the input is decreasing, the output does not follow the increased path. So it is having some deviation. So this particular deviation we can call it as an hysteresis. Hysteresis, because we have some springs in the measuring instrument, and those springs, when it is increasing, that means when it is loading, the springs will be expands to the upper input. But when the input is decreasing, the springs does not compress that much of increasing. Okay, so because the stiffness of the springs does not come back to its actual value when it is decreasing. So here we have two cases, one is increasing cases and another one is decreasing case. Input is increasing and the input is decreasing case. When the input is, see here the second figure, so when the input is increasing, up to here increase, and output is also increasing, again input is decreasing and negative came, and output is also changes, again input is increasing, the output does not, output is deviating, actually should follow the same value in this one, but it is deviating, so it means it is having some hysteresis. So this deviation, when the input is increasing and output input is decreasing, the output does not follow the same manner, so that can be considered as an hysteresis. Is because of internal friction and hysteresis damping, the output is not same for both increasing and decreasing values of the instrument. The fact that the energy put into the stressed parts when loading cannot recover back when unloading. Okay, this is the reason the hysteresis is forming. So when increasing stays, increasing the input, in such situation we are applying some stress on the parts. When decreasing, those stressed parts not come back as, so that's why the increased value and decreased values are not matching. So that variation will be considered hysteresis. This hysteresis value should be low for the instruments, then only it will produce as the correct value. And coming to reproducibility. Reproducibility, it is the degree of closeness with which a given value may be repeatedly measured. So reproducibility. So the measured value should have produced the same value of input. So that should have some uh, same value. So we are measured number of times. So it should produce the same value. That is reproducibility. Okay, it may be specified in terms of units per given period of time. So for a given period of time, how it is produced at the same value will be considered reproducibility. And repeatability. Repeatability is defined as the variation of the scale reading and is random in nature. So repeatability. See here, actually this is the actual measured line, but repeatability means, so it should be produced, it is producing at this output is producing in this manner. Okay, so for the number of times it repeat the same manner, it should be produced the same manner of the output, then we can say it is a having a repeatability. So reproducibility and repeatability are the measure of closeness with which a given input may be measured over and over again. So number of times we are measuring, so it produces the same value, so that will be very closer to the actual value. So that represents the reproducibility and repeatability. Okay, and coming to drift. So perfect reproducibility means that the instrument having no drift. So no drift means that with a given input, the measured values do not vary with the time. Means that with a given input, for a given input, the measured values do not vary with time. Okay, so it should be produced same input. It does not vary. Okay, drift classified into three categories. The first one is zero drift. This is the zero drift. See here, this is the graph for the normal characteristics. So it should be produced like this. But when the input is applied, the output is shifted at zero input. So input is, when the input is zero, so we have some output. So this is the this difference of output is known as the zero drift. So that is input and follows the normal characteristics. When the instrument is calibrated, then it is called as zero drift. When we are calibrating an instrument, it should follow this line. But due to some springs, uh, sp- uh, spring systems, it does not follow the actual actual characteristics. It is having some input value initially, so this will be removed by resetting. This zero drift will be removed by pressing the reset button in the instrument. And coming to span drift or sensitivity drift. So if there is a proportional change in the indication all along the forward scale, the drift is called as span drift or sensitivity drift. So see here, this is the span drift. So this is the normal characteristics we have to follow, but characteristics with span drift. So in this case, the um, the characteristics are started with zero, but it does not follow in the normal characteristics. It is deviating. It is deviating this much of amount with the normal characteristics due to span drift. Span drift. So at the output final value of the final value, there is some variation with the normal characteristics. Whereas in this case, at the initial value, only there is some deviation with the normal characteristics, and it is following this characteristics as it is. It is following this characteristics as it is, but it is having initially some drift values there. But here in this case, see initially it is following as normal characteristics as zero, but at the final stages, for the coming to the final stage, this value is changes. This value is changing, not following the actual characteristics. So that's why this is called as span drift. So and in some cases, instrument having both the zero and the span drift. So see here. So initially this is having zero drift and it is not following the normal characteristics. It is deviating and it is changing at the span. So this is the representation of the characteristics having both zero and span drift. And next one is zonal drift. So zonal drift means at a particular zone of the uh, uh, curve we are having a deviation. So in this case, drift occurs only over a portion of the span of instrument. It is called as zonal drift. There are many environmental factors which causes this drift. So what are the factors which causes the forming of this drift means? So here the number of factors which influence the formation of the drift. So the first one is stray electric and magnetic fields, thermal EMFs, changes in temperature, mechanical vibrations, wear and tear problems, high mechanical stresses developed in some parts of the instruments and systems. So because of these particular values, these particular cases, due to this the um, systems are producing a drift. Okay, so now I am stopping at this time, at this point. So mm, so now I am taking the attendance. Please stay on the line. What is the roll number of Srinivas Rally? Hello? Roll number of Srinivas Rally.
443, sir.
443. Okay. Okay, I was taken the attendance. So coming to again the subject. So linearity. The another important characteristics of static characteristics of an instrument is linearity. So one of the best characteristics of an instrument or measurement system is linearity. That is, the output is linearly proportional to the input. So in this case, linearity is defined as ability to reproduce the input characteristics symmetrically and can be expressed as all of you know that y is equals to mx plus c. So y is the output, x is the input, and m is the slope, and c is the intercept. So you see here, this is the idealized straight line. So this is the actual calibration curve. So this calibration curve should be follow the straight line, but it is some deviating with the idealized straight line. So this much amount of variation. So maximum deviation. So this maximum deviation will produce as the non-linearity. So the linearity is expressed as a percentage of the departure from the linear value. Okay, how much the maximum value of the curve is deviated from the linear curve, so that can be considered as maximum deviation. Okay, and that is the maximum deviation of the output curve from the best fit straight line during any calibration cycle. So the non-linearity, so the non-linearity may be due to the non-linear elements in the device. So the non-linearity will be produced due to the non-linear elements present in the device. The percentage of non-linearity is maximum deviation of output from idealized straight line to actual reading in terms of percentage. So linearity is one of the important characteristics. So it should be follow the input. The output should follow the input. So then only you can get the linear output. So if there is any deviation, so that produces the non-linearity. This non-linearity will be causes because of the non-linear elements present in the device. And these are the static characteristics of an instrument. Okay. So if you have any doubts regarding this topic, you can type in the chat room. So there is a chart option is there. The chart we can type your if you have any doubts regarding any topic which is discussed now up to now. Okay. So if you I think all of you paid the fees. If anyone is not paid the fees, so please pay the fees. Okay. Thank you. I am closing the session.